Download this code from codegive.com, link in the description below. Diving into the divide by zero error on 1970s vintage calculators, a deep dive. The 1970s was a golden era for calculators. Solid-state electronics became affordable enough to bring these computational marvels to homes and businesses. While these calculators could perform basic arithmetic operations, they were also known for their quirks, limitations, and, most notably, their handling of the infamous divide by zero error. This tutorial will explore how these vintage machines handled this classic mathematical problem, providing insights into their internal workings and demonstrating a simplified, conceptual code example. The context: 1970s calculator technology. Before we delve into the error handling, let's understand the technological landscape. Hardware integrated circuits, ICS calculators were built around custom ICS, often referred to as large-scale integration, LSI, chips. These chips contain the logic gates, arithmetic logic units, ALUs, and memory necessary for calculations. Displays LED, light-emitting diode, or gas discharge, Nixie tube, displays were common, often using 7-segment displays to represent digits. Keyboards, basic numerical keypads and function keys, plus, dash, asterisk, slash, smiley face, power, typically battery powered or AC powered. Software, firmware. Microcode / hardwired logic. These calculators didn't run a general purpose operating system. Instead, the calculator's behavior was dictated by microcode, a sequence of instructions stored in ROM, read-only memory, or even implemented directly using hardwired logic. This microcode defined the steps for each operation. Limited memory. Memory was scarce and expensive. Calculators stored only a few numbers, usually 1 or 2 for immediate calculations, and often employed clever techniques to minimize memory usage. BCD, binary-coded decimal numbers were typically represented using BCD. Each digit, 0 to 9, was represented by a 4-bit binary code. This made displaying numbers easier but could be less efficient for internal calculations than pure binary. 2. The divide by zero problem. In mathematics, division by zero is undefined. It leads to logical inconsistencies and breaks down many fundamental rules. A naive approach to computing x/0 would result in either 1 infinity if you treat division as the inverse of multiplication, finding a number that, when multiplied by 0, equals x, where x is non-zero, is impossible. 2 an undetermined value if you define it as a limit, approaching 0 from positive or negative values gives results of plus infinity or dash infinity, which are not definite values. 3. How 1970s calculators handled divide by zero. The approach taken by 1970s calculators to address this issue varied between models and manufacturers, but some common patterns emerged. Error indication. The most common approach was to display an error message. This message would be displayed instead of a numerical result. The exact error message would depend on the calculator. Examples include *E, for error. *Error, if the display was alphanumeric. *A blinking display. Overriding the display with a special character pattern. Freezing. Some calculators would freeze after a divide by zero error. The display would show the error, and the calculator would become unresponsive until a specific reset key or sequence was pressed. Ignoring the error, potentially incorrect results. Rarely, and usually in very early or poorly designed models, a divide by zero operation might result in garbage output or an unpredictable state. The calculator's internal state could become corrupted, leading to further incorrect calculations. This was undesirable but could happen due to limited error checking. Asterisk handling 0 divided by 0 asterisk. This case presented a special challenge. Some calculators treated 0/0 as an error like any other divide by 0. Others might, perhaps mistakenly, return 0 or an indeterminate value. 4. Why these approaches? Limitations and trade-offs. The engineers designing these calculators faced significant constraints. Asterisk processing power asterisk. The ALUs were relatively slow and had limited instruction sets. Complex error checking routines would significantly increase the calculation time and the complexity of the microcode. Asterisk memory constraints asterisk. Storing extensive error messages or complex error handling logic would consume precious memory. Asterisk display limitations asterisk. The displays could only show a limited number of characters, often just numerical digits. Expressing complex error messages or scientific notation was impossible on most models. Because of these limitations, the chosen approach was typically a balance between functionality, performance, and cost. A simple error indication was often the most practical solution. V. A simplified conceptual code example, Python simulation. While we can't directly access the microcode of a 1970s calculator, we can simulate its behavior using a modern programming language like Python. This is a very simplified and conceptual example to illustrate the core logic. It doesn't perfectly replicate the exact behavior of any specific vintage calculator, but it captures the essence of how division and error handling might have worked. Explanation of the code asterisk. One vintage calculator class asterisk represents the calculator. 2 __init___ method asterisk initializes the calculator state. Asterisk display _size simulates the limited display of a vintage calculator. Asterisk accumulator holds the current numerical value. Asterisk error _flag indicates if an error has occurred. Asterisk display, the string representation of what is shown on the display. 3 clear, method asterisk resets the calculator to its initial state, clearing the error. 4 enter _number, method asterisk simulates entering a number via the keypad, storing it in the accumulator. 5 perform _operation, method asterisk handles arithmetic operations. Asterisk checks for a pre-existing error. Asterisk performs the requested operation, plus, dash, asterisk, slash. Asterisk divide by 0 check asterisk specifically checks for division by 0, if divisor equals 0.0. If detected, it calls the show _error, method. 6 equals, method asterisk completes the calculation and displays the final result. 7 show _error, method asterisk sets the error _flag to true and displays an error message on the simulated display. 8 update _display, method asterisk a simple way to show the display's content. Key aspects demonstrated asterisk. Asterisk error flag asterisk the error _flag is crucial. Once an error occurs, the calculator refuses further operations until it's cleared. This mimics the frozen state of some vintage calculators. Asterisk divide by 0 check asterisk the code explicitly checks for division by 0 before performing the operation. Asterisk limited display asterisk the update _display function truncates the output to the display _size, simulating the limited display capabilities of a 1970s calculator. 6. Beyond the basics, further considerations. Asterisk floating point representation asterisk this example uses Python's built-in floating point numbers. Vintage calculators used BCD and fixed point arithmetic, which would have affected precision and the handling of very large or very small numbers. Asterisk more detailed error handling asterisk a more sophisticated simulation could include different error codes and specific error messages for various types of errors, overflow, underflow, invalid input, etc. Asterisk chain calculations asterisk vintage calculators often had quirky behavior when chaining operations. For example, 1 plus 2 plus 3 equals might not always work as expected. Simulating these nuances would require a more complex state machine. Asterisk memory management asterisk the simulation doesn't explicitly manage memory limitations. A more accurate simulation would need to track how memory is allocated and used. Asterisk Nixie tube simulation, optional for a more visual effect, you could use a graphics library, like Pygamy, to simulate the appearance of a Nixie tube or 7-segment display. 7. Conclusion. The handling of the divide by zero error in 1970s vintage calculators provides a fascinating glimpse into the trade-offs made in early solid-state computing. Limited processing power, memory constraints, and display capabilities forced engineers to prioritize simplicity and efficiency. While the error handling might seem rudimentary by modern standards, it was a pragmatic solution that allowed these calculators to perform basic arithmetic functions reliably. By studying these vintage machines, we can appreciate the evolution of computing and the ingenuity of the engineers who pioneered this technology. Remember that this is a simplified simulation, and the actual behavior of specific models could vary significantly. However, the core principles of error checking and limited resources remain relevant to understanding the development of early calculators. Remember to research the specific model of calculator you're interested in for more accurate details.